The last video got a bit technical and I didn't like that, so I hope this one would feel more visual and intuitive, and it probably will because we'll be talking about orbital shapes and chemical bonding. Electrons sometimes act as waves, which means that they don't have a precise location. Even if they do, we wouldn't be able to predict it because of the uncertainty principle. So electrons, according to particle physicists, are clouds of probability, areas where the electron probably is. This is called an orbital. There can be many types of orbitals, but scientists only care about 4. You met them in the last video. They are S, P, D and F. In fact, we would probably only need to learn about the first 3. The shapes of these orbitals are calculated using Schrödinger's equation. Let's look at how these orbitals look. The s orbital is symmetric in all directions, meaning there's an equal probability of finding an electron in any direction. Can you guess the shape of it? It's a sphere. The p orbital has 2 lobes in opposite directions, which means that the probability of finding an electron anywhere is close to 0 except a straight line. This shape is called a dumbbell. I don't think the people who named it have ever been to a gym, cause that does not look like a dumbbell, but who am I to judge? Now, you may realize that this line can reside along one of the 3 coordinate axes of 3D space x, y or z. And that's because there are 3 orbitals or rooms from our previous analogy in the p apartment. Each orbital can hold 2 electrons. Now comes the d orbital. Its shape is called a double dumbbell and it covers an entire plane. So we have xy, yz and zx orbitals. But you might be thinking that there are 5 orbitals in the d subshell, right? And that is correct. The last 2 are called x squared minus y squared and the z squared orbitals. The first 3 lie in the plane at a 45-degree angle to the coordinate axis, while the last 2 lie on the coordinate axis. Now that we know how these orbitals look like, we can finally learn how they come together and form covalent bonds. And for that, we must understand a concept called hybridization. Now what you are going to hear will sound very strange, so I want to talk about how scientists come up with theories. You have a bunch of experimental data and you try to find the story that explains why you have the data that you found. That's what a theory is. And sometimes they sound crazy or illogical, but if it works, it works. According to this theory, atomic orbitals before they form bonds combine with each other and form something called hybridized orbitals. And these orbitals are the ones that take part in chemical bonding. Only the orbitals that would take part in bond formation hybridize though. All other orbitals are left untouched. These orbitals look something like this. The orientation of these hybridized orbitals depend upon how many atomic orbitals fuse to form them. And we can understand that using the valence shell electron pair repulsion theory, or VSEPR for short. The first geometry on the list is sp hybridization, which is made up of one s and one p orbital. This means that the other 2 p orbitals of that shell are in their place untouched. It has a linear shape. Next is sp2 hybridization, which is made up of one s and 2 p orbitals. It has a triangular shape in a plane with a lone pure p orbital perpendicular to it. Then comes sp3, which is in the shape of a tetrahedral. After that comes sp3d, which along with 1s and 3p orbitals also has one d orbital hybridized with them. Its geometry is called trigonal bipyramidal. After that comes sp3d2, which has an octahedral geometry that looks like the coordinate axis. And finally, we have sp3d3, whose geometry is called pentagonal bipyramidal. VSEPR theory helps us understand the shape of a molecule, which is very important in organic and biochemistry. The bonds formed by overlap of these hybridized bonds is called sigma bonding. There is another type of overlapping called pi overlap, which happens with the bonds that are not hybridized. As you can imagine, sigma bonding gives the molecules free space to rotate within that axis, but a pi bond restricts that motion and locks its spin. It is important to note that only half-filled hybridized orbitals can form sigma bonds. These orbitals must have one electron in them. An empty orbital and a full orbital can form a bond, but that type of bonding is called a coordination bond and it puts a positive charge on the donor atom called a Lewis base and a negative charge on the receiver atom called a Lewis acid. If an orbital is full, it has 2 electrons in them, and so it's called a lone pair. Lone pair along with sigma bonds form something called a steric number, which determines the geometry and hybridization of a molecule. It is equal to the number of atomic orbitals hybridized. That was chemical bonding in a nutshell. Now, let's look at some specific examples to learn this topic better so we can finally talk about organic chemistry. Let's look at CH4, which is also known as methane. Looking at the configuration of carbon, you might think that it has only 2 half-filled orbitals. Then how can it form 4 bonds? And the answer to that question is that one electron from 2s orbital jumps to fill an empty orbital in 2p. So now we have 4 empty orbitals which hybridize into an sp3 configuration ready to bond with 4 hydrogen atoms in a tetrahedral geometry. But I must warn you that we can only jump electrons like this when the energy gap between the orbitals is not big. And it turns out that the energy gap between 2p and 3s is big enough that electrons can jump between them on their own. So, carbon, nitrogen, oxygen and fluorine cannot have higher steric numbers than 4. Because of their lone pairs, carbon must form 4 bonds, nitrogen must form 3 bonds, oxygen must form 2 bonds, and fluorine can only form 1 bond. This, however, does not happen for other elements as they have access to the next d orbital, which is close enough in energy that they can show any hybridization possible. Thanks for watching, and I'll see you in the next episode.